Morning, everybody, and welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 12, and then we are going to finish off our discussion of Standard 13, looking at unconstrained optimization. If you're wondering what the word unconstrained means, by the way, we're going to see what that means in Standard 14 when we talk about constrained optimization, which is similar but slightly different. As far as office hours go, keep in mind the next time we're actually going to be meeting is Wednesday a week from now, because we have classes off Friday and Monday due to the Easter long weekend. I will be around Thursday of this week and Tuesday of next week, so if you want to come by my office hours, they'll be at usual times, 10 to 11 and from 1 to 2. Also at my usual office hour this afternoon from 2 o'clock to 3 o'clock. I will not be holding my usual office hour, though, on Monday, so keep that in mind. And as far as homework goes, we will plan on doing the Standard 13 quiz Wednesday after you get back. Couple comments. I just passed back the exam 2s. I'm happy to meet with you one-on-one to talk about them. Just feel free to come by my office hours or set up an appointment. Overall, those went pretty well. I noticed some of you, I think, were a little bit too ambitious, tried to answer like 10 questions or something on it. Like I said, I purposely write these exams with the idea that you're able to do, that you have time to do about 6 questions on them each. So, encourage you in the future with exams going forward, try not to spend too much time on, or not too much time. Try not to do too many questions on the exams that you're not giving yourself enough time to do the ones that you're trying. I think it's good to kind of keep a healthy balance. It's better to try 6 standards and get masteries on all of them rather than trying 10 and only getting masteries on, say, 3 of them. Just in terms of how stressed out it will make you and such. And how many masteries you'll have going forward. Next exam, by the way, I haven't exactly decided when that's going to be, but I'm probably going to make an announcement over the break on that. It's probably going to be not next week, but the following week sometime, I would guess. But I'll let you know once I've got a chance to think about this over this long weekend. Does anybody have any questions or comments before we get started for today? Okay, in that case, an engineer, a physicist, and a mathematician are all subjects in a psychology experiment. After not eating for 24 hours, each of them is locked in a room with a can of food, some paper and pencil, but no can opener, and no real way to open up the can. So they're locked in this room, kind of starving for a while. And at the end of the experiment, psychologists first go into the engineer's room. The pencil and paper are unused, but there are dents all over the walls. Turns out the engineer just threw the can into the walls over and over until eventually it split open. And engineer's having a rather dented but still delicious meal. They go to the physicist's room next. The paper this time is covered in formulas, and there's only a single dent in the wall. And the physicist is eating from the can. Turns out the physicist calculated the perfect way to throw the can against the wall and got the can to open up with just a single throw. And last, they go to the mathematician's room. In the mathematician's room, the paper is full of formulas, there are no dents in the wall, the can is still closed, and the mathematician is nowhere to be seen. But psychologists realize that there's some strange noises coming from the can. So psychologists quickly grab a can opener, open up the can, and out pops the mathematician. And she says, "Oh, thank goodness, thank you for saving me from this can. I was trying to figure out how to open up the can, and I accidentally got a negative sign wrong." Okay, in that case, I'm going to go ahead and pass out the quiz. You all know the drill. Let me know if you have any questions on this. Yeah. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please. Okay, so you may recall from class on Monday when we started Standard 13. On Monday, we talked about what it means for a set to be compact, closed, and bounded. We talked a little bit about the extreme value theorem, part 2, which gives us conditions under which we can find absolute maxima and absolute minima of a function. And then we started looking at an example which I want to finish up in today's class. So the theorem, you may recall, says that if f is a function from Rn to R, and if f is continuous over some compact set S, then f has to have an absolute max and an absolute minimum over S. Can anybody remind me, what did we mean when we said that, when we talked about a set S being compact? S? Exactly. So we said that S is compact if it's closed and bounded, where closed meant that the set contains all of its boundary points, so all the points on sort of the edge of this set. So for instance, in this case, for this triangle T, we know that this is a closed set because we're including all the points on the edges of the triangle. And bounded means the set doesn't go off forever in any direction. It doesn't extend outwards towards infinity, which for this set T, it's this nice kind of compact triangle, doesn't head out. It doesn't head out forever in any one direction. So this would be an example of a compact set. And if you have your function is continuous over S, and S is a compact set, then the extreme value theorem part 2 said that f has to have an absolute max and an absolute min. Meaning you can find points a min and a max within your set such that f of a min is the smallest output out of all the potential outputs you could get from plugging in points in your compact set, and f of a max being an absolute maximum value means this output is going to be greater than all of the other outputs over the infinitely many points within your set. And according to the extreme value theorem, we had 3 potential points where these absolute maxima and absolute minima could occur. At critical points of f that happen to lie inside of your set, at the corners of your set, and this mysterious third one we didn't really talk much about on Monday, which is critical points when f is only considered along the boundary pieces. And that's going to be the one that we're going to focus on today. So the example we had started to look at last time was we're given this metal plate T, this triangular metal plate, and if f of xy is a function that tells us what is the temperature at any point on the plate, or at any point xy on the plate, it's x squared plus xy plus y squared minus 6y degrees Celsius. our goal was to find the hottest point on the plate and the coldest point on the plate. In other words, at what point on our plate does our temperature function have an absolute maximum, and at what point does it have an absolute minimum? So our goal was to go through and find all of these possible locations, to find all of the potential points at which we had an absolute max and an absolute minimum. So I forget where we got to in this section. Did we find the critical point of f inside the set? So I won't go through that again, but I'll just list it out as critical point of f in t. We found one point, which was the point -2, 4, which we found by taking the derivative of f, by taking del f del x and del f del y, setting them both equal to 0, and solving for both x and y. When we did that last time, we got a single point, -2, 4, which did happen to lie inside of the set at about the point there. Our second potential point was looking for the corners of the set T. Since we have a triangle, this looks like the set is going to have 3 corners to it. Jacob, where's the set going to have corners?
It looks like -3, 0, 3, 0. Would be -3, 6.
Looks that way. How did you get 6 for the y coordinate at this point?
I don't remember. I had it written down from last time. I said, oh,
we already
the equation of that line.
Yeah, I think
Y equals 3 minus x. You just plug in -3, 4x.
I agree. So it's this line right here that's kind of making the top boundary of our triangle. It's just the line y equals 3 minus x. If this point right here has an x-coordinate of -3, find the y-coordinate, just plug it out into the line. 3 minus -3 will give us a y-coordinate of 6. And so that's kind of part 2 of the different points which could be our locations of absolute maxima and absolute minima. And today, I want to focus on this third possible location for where can we have an absolute max and an absolute min, which is critical point when f is only considered along the boundary pieces of S. This one, I think, is kind of the trickiest of the 3 different types of locations. So, first of all, Madeline, how many different boundary pieces would you say that this triangle has? In other words, how many sides does it look like we have? 3 sides to a triangle. I'm going to label these 3 sides E1, E2, and E3, where E1, E2, and E3, just E stands for edge. So E1 is going to be the bottom edge of this triangle, E2 is going to be the edge on the left, and E3 is going to be the hypotenuse, this edge on the top of our triangle. And our goal is going to be to see what happens if we look at how our function f of xy behaves when we only are looking at the points on one of these individual edges. So let's start off with the edge E1. What do we know about all of the points on E1 here? They all are going to share some characteristic in common with each other. Everybody tell me what we can say about every point on that specific segment. In particular, something about their coordinates. Yeah?
The y-coordinate is always going to be 0.
Yeah, the y-coordinate is always going to be 0. That's kind of what's special about the points on E1 as opposed to the rest of the triangle. So on E1, we know that the y-coordinate is going to be 0. And if we look at what is f of xy going to do on that segment, well, along that segment, we could just plug in y for 0. And if we do that, we'll get that f of x comma 0 is going to be x squared plus x times 0 plus y squared is 0 squared minus 6 times 0, which when we simplify that down, it's going to simplify down to just the formula f of x equals x squared. And what that means is that if you want to look at any point along this bottom edge, E1, and you want to take any point along E1 and plug it into our function f of xy, our temperature function, all that we really need to do is to take the x-coordinate of any one of these points and square it. Because all of the terms with y's in them, specifically for points on E1, all the terms with y's in them are going to go to 0. Because you plug in a 0 for y, it goes to 0. 0, 0. The only non-zero term, 4 points on the edge E1, is x squared. And so what we're going to do is specifically looking at the bottom edge E1, only the points along here, we can rewrite our temperature function as just behaving like the function f of x is equal to x squared. Doesn't work for points elsewhere in the triangle, in the center or along the other edges of the triangle, but on the edge E1, the temperature function behaves just like this one. And so ultimately, when we're looking at step 3, we're asking the question of where can we find critical points when f is only considered along the boundary pieces of S. What we really mean is we're asking the question of if we rewrite our function to see how it behaves along a single boundary piece, so along E1 it behaves like f of x equals x squared, what's going to be the critical points of this function as seen here. And the cool thing is, we've taken a Calc 3 function, f of xy equals blah blah blah, and this is now a Calc 1 function. Just f of x equals x squared. Let's see. So Bennu, if I were to ask you in a Calc 1 setting, we have a function f of x equals x squared, we want to find its critical points, what would you do?
I would say it equal to 0.
You would say that again?
Set it equal to 0.
Just set f of x equal to 0?
Yeah. Like x squared equals 0. So it equals 0.
Technically that will give you the correct answer, but in general, when we're finding critical points, we're not looking to set the original function equal to 0. I think we need to do what first? No? Yeah. I think we're going to need to take f prime of x first and set that equal to 0, and then solve for x. For this specific function, it'll give you the same answer either way, namely x equals 0, but in general, it will not. So here, we can take f prime of x and get f prime of x equals 2x, which we can set equal to 0. And if we do that, we solve for x, we end up finding x equal to 0. Dr. Gerstel, what's up with this prime notation? I thought you told us in Calc 3 we can't use that. We have to use like del f del x or something. So why is it specifically okay for this function f of x to just use f prime instead of having to take like a partial derivative del f del x, like we normally would if we differentiate with respect to x? Emily? Yeah, because specifically this is a function of only one variable, so when we differentiate, well, f prime of x is the only... differentiating with respect to x is the only way that we can do it. Whereas if you compare that with this function, you could differentiate with respect to x or with respect to y. And so here we would have to specify del f del x or del f del y. But here it's okay to just say f prime because there's no confusion. This is only a function of x, so we have to differentiate with respect to x. And it turns out at x equals 0, we're going to get a critical point for the function f restricted to the edge E1. So at the point xy equals 0 comma something, f of xy has a critical point when restricted to the edge E1 in our triangle. By the way, we picked a point whose x-coordinate is 0 on E1. We found that on this edge at x equals 0, we have a critical point. What's going to be the y-coordinate of that point? Brown?
0.
Why is that? Other than the fact that it looks very much like I drew a dot at the origin.
Because we're on the boundary, like we stated when we originally wrote on E1, all the coordinates on this boundary have a y-coordinate of 0.
Yeah, that's exactly right. Since we know that every point on E1 has to have a y-coordinate of 0, that means that the point on E1 that has an x-coordinate of 0 has to be the origin, 0, 0. It's the only point on E1 that has an x-coordinate of 0 because every point on E1 has to have a y-coordinate of 0. And so when we do this, when we find critical points on the different boundary pieces, this is going to give us another potential location for where f of xy could have an absolute maximum or an absolute minimum according to the extreme value theorem. So I'm actually going to write that down over here, where if we're looking for critical points on boundary pieces, we found a critical point on E1 at the origin, which is going to give us another potential location for max or min. We restricted our function f and saw how does f behave on point on E1 specifically. Behaves like f of x equals x squared. We took critical point of f of x equals x squared, got x equals 0. And so that means that at that point, f of xy, our original function, restricted to the boundary, is going to have a critical point there. And that's what condition number 3 here actually means for possible locations of absolute extrema. So let's look at it. So we need to repeat this process for each of our boundary segments. You have E1, E2, and E3. We're going to need to go through this for each one. So the next one I want to look at is on the segment E2. Let's see. Holly, what do we know about all the points on this left side of this triangle? What can we say about their x or y coordinates? Yeah, all the x coordinates are -3. And so what we can do is we can set up and do something very similar. On E1, we knew all the y coordinates were 0, so the function behaved like f of x comma 0 there. On E2, we can do something a little bit different, which is to take f of -3 comma y instead. We could say, well, everywhere on E2, whenever we plug in the x coordinate into our function, it's just always going to be -3. And so, let's see. Lindsay, if we were to take f of xy and swap out all of our x's with -3's, what's that going to give us?
We'll have 9 -3y plus y squared minus 6y.
Like that? Sorry, I look at Brianna, I don't know why. Does that look good? I like it. Yeah, we just swap everywhere we see an x, we're going to replace it with -3, because on this boundary segment, E2 here, all of the x coordinates happen to be -3. And we can simplify that down to saying it behaves just like the function f of y equals y squared minus 9y plus 9. We take -3 squared to get 9, and -3y minus 6y will combine to give us a -9y. So in other words, if you wanted to find the temperature, plug into the temperature function any point on E2 we know that the temperature is just going to be equal to the y coordinate squared minus 9 times the y coordinate of that point plus 9. Sean, if we wanted to find critical points then of this function f of y, what would be a good first step? Y minus 3. Like that? Is that okay to do? Well, I see you shaking your head.
No, it'd be minus 6.
Yeah, I think the problem with this is if we were to multiply this out, it would give us a y squared, a plus 9, but we'd get a minus 3y minus 3y is minus 6y instead of minus 9y. It actually turns out to be the case. This function, this f of y doesn't really factor very easily. So what could we do instead if we wanted to find our critical points? Mel? Yeah, I think we can do the same thing we did here. Just take the derivative, set it equal to 0, solve for y. By the way, Mal, with respect to which variable are we taking the derivative?
Y.
Yeah, because this one is only a function of y, so this time we're going to be differentiating with respect to y. Since it's the only variable again, though, it's okay to just say f prime of y. So f prime of y is going to be 2y minus 9, it looks like, which when we set that equal to 0 and solve for y, what is that going to give us? What?
Y equals 9 now.
We would get 2y is equal to 9, divide both sides by 2, y is equal to 9 halves. That tells us, at this point here with a y-coordinate of 9 halves, f of xy is going to have a critical point on the segment E2. What's going to be the x-coordinate of that point? Sarah?
-3.
I think it's going to be -3 because we know that to be true of every point on E2, that left edge, that the x-coordinate is always -3. Let's see. Laurie, I have a question for you. Do we actually know that -3 comma 9 halves is going to be on E2 and that it's not going to be, say, above the line or below it? Because that would be bad if we found a critical point, a point that we want to include as a place to check, and it's not actually within our triangle.
I think it will be on because the top corner of the triangle is at -2 space, and 9 has a 1 space.
So the y-coordinate 9 halves is going to come between 0 and 6? Yeah, I agree. Technically, when we go through this procedure and find critical points of f restricted to E2, we're really looking at f restricted to this entire vertical line here, the line x equals -3. And so we actually need, one thing we need to do is to actually go through and check, do our critical points actually lie on this edge of the triangle rather than somewhere up here or somewhere down here. But as Laurie pointed out, since the y-coordinate of this point, 9 halves is 4.5, is between the y-coordinate here of 0 and the y-coordinate of 6, it's going to turn out that this point does in fact lie on our E2, and so it is a point we need to consider. So we're going to get another point to consider on E2. When we restrict f to E2, we're going to have a critical point at -3, comma 9 halves. And that'll be another place where f of xy could potentially have an absolute max or an absolute. John, we found a critical point on E1. We found a critical point on E2. What should we check last for our last potential place for absolute max and min to occur?
Look for critical points on E if we've done the other one that we have not done, which is going to be E3.
All right, let's check E3 for critical points. Is everyone all right if I erase the E1? So now, the last place where we could potentially look is on the top line E3. What do we know about points on this line segment, on this diagonal line? That one's going to be a little bit trickier because this time we can't just say x coordinates are constant or y coordinates are constant, because as we go along this line, our points are going to have different x and different y coordinates. Sarah, any ideas?
The equation of the line is y equals negative x plus 3.
Yeah. So instead of saying y equal to constant or x equal to constant on that line, we could just replace our y coordinates with 3 minus x or negative x plus 3, as you said it instead. So this time, instead of just plugging in a number for x or a number for y, what I want to do is we're going to take f of x comma 3 minus x. We're going to use the fact that for every point on E3, the y coordinate is always 3 minus the x coordinate. And so something we can do is we can just take our formula for f of xy and replace all of our y's with 3 minus x's. Which if we do that, we'll get x squared plus x times 3 minus x plus 3 minus x quantity squared minus 6 times the expression 3 minus x. If we had wanted to, we could solve y equals 3 minus x for x and say x is equal to y plus 3, and then just replace all of our x's with y plus 3 instead, and it would end up giving us the same results in the end. It would just write everything in terms of x instead, or y, excuse me, instead of writing everything in terms of x. So we simplify this, we'll get x squared plus 3x minus x squared. Golly, how do we FOIL? Plus 9 minus 6x plus x squared minus 18 plus 6x. Swoosh, swoosh. Swoosh, swoosh. X squared plus 3x. Plus 9 minus 18. I think this is going to simplify in the end to the expression x squared plus 3x minus 9. Meaning, for any point on E3 along this line segment, you can plug that point into the temperature formula, f of xy, and what would pop out is going to be x coordinate squared plus 3 times x coordinate minus 9 every time. So now we can do the same thing we did for E1 and E2. We can differentiate, set it equal to 0, and find our critical points. We differentiate this time. We'll get 2x plus 3 is equal to 0. Let's see, who got it yet? Gary. We were to set 2x plus 3 equal to 0 and solve for x. What is that going to give us?
Should be negative 3 over 2.
2x equals negative 3, x equals negative 3 halves. I like it. So, just like in the previous two, we found a critical point at negative 3 halves. And so that's going to tell us that at the point with an x-coordinate of -3/2, f of xy has a critical point when restricted to E3. How do we find? Yes, Luke?
Then wouldn't you just plug in -3/2 into the y equals 3 minus x, and you would get your y coordinate?
Couldn't have put it better myself. It was nice job predicting my question. So yeah, if we want to find what's the y coordinate at this point, well, we know it has to be 3 minus the x coordinate, and 3 minus -3/2 is the same as 6/2 plus 3/2, which is going to give us 9/2. Ix. Do we know if -3/2, 9/2 actually lies on E3? Meaning, do we know it doesn't lie like down here or up here somewhere on that line? How do we know? Yeah, I think since the only thing we really need to worry about is the x coordinate between -3 and 3. Because we already know the y coordinate's going to be equal to 3 minus x. That one's okay. Is -3/2 between -3 and 3? I think so. -3/2 is -1.5, and so our point at E3, -3/2 comma 9/2 is going to give us a point that's actually on our edge E3 here. All right, we found all of our critical points along the boundary pieces. In this example, we found one on each edge. In general, you could have multiple multiple critical points on a single edge, or you could potentially have none at all. In that case, you just include any that you find in the list, any that you find that also happen to satisfy the conditions of the initial set. We had to go through and check each one of these to make sure they do lie on the edge we say they do. And turns out for each one in this case, we had one critical point that fit the bill. But if you had more or fewer, you would just include all of them that you find. All right. According to the extreme value theorem, the absolute maximum of the function f on the set T and the absolute min have to occur at one of these 7 points. So the question becomes, how can we tell at which points do we get an absolute max and an absolute min? Extreme value theorem tells us it has to be within, the max and min have to be within these 7 points right here. It doesn't tell us which one specifically, though. Does anybody have any ideas for how we could actually go through and find which one's a max, which one's a min?
Well, maybe start with doing maybe start with finding out which are local maxes and local mins. At least then you'll eliminate any saddle points, and then then I guess you can compare like which local max is taller, which local min is smallest.
Okay, we could restrict ourselves. We could get rid of the saddle points by checking each one of these. Really don't want to have to do the second derivative test 7 times if I can help it, because that sounds like a lot of work. Katie?
You just plug it into x y is x squared plus x y squared minus 6y.
Okay, so just plug all of them into the function, and then what?
And then you can just see whether the output is bigger or smaller.
Okay, so Katie wants to do the brute force approach, where we just chuck all of these 7 points into the function, see which one's biggest, which one's smallest. And I think that's going to be what I'd like to do as well. I think that's a good approach to it. Look, what you proposed actually should work. It's just going to be a lot more work to eliminate saddle points. I think the simplest thing to do is just plug them all into the function, see which one's biggest, which one's smallest. If you wanted to, you could eliminate saddle points by checking for those first, but checking for saddle points I think is just more work in general than just plugging them into the function. So I think I'm going to take Katie's approach, but what you said should work as well. So the way I like to do this is to make a table. I'm going to put in a table, which at the top, we're going to have the points x, y, as well as their outputs. So let's see, we found one critical point inside of the set T, which was -2, 4. We found 3 corners, which were at -3, 0, 3, 0, and -3, 6. And we found 3 critical points along the edges, where those happen to occur at 0, 0, at -3, 9 halves, and at -3 halves, 9 halves. Save us the trouble of having to go through and calculate. I'll just tell us what f of xy is for each one. At -2, 4, we get an output of -12. At -3, 0, and 3, 0, we get outputs of 9. At -3, 6, we get -9. 0, 0, we get 0. The last two, we're going to get -11.25. So all of these numbers I got by plugging in these 7 points into the original function for f of xy. So, especially plugging in these last two kind of makes some nasty expressions plugging this in. This is a quiz or an exam question. It would be nicer numbers for you to work with. But in this case, this is what it comes out to. All right, Katie, you proposed the method, so you get to interpret the results.
Looks like we have 2 absolute or equal absolute maxes, which I'm not sure if that means there is no absolute max, but at -3, 0, 0, and an absolute min at -2.
Yeah, so it looks like we have no problems with absolute minimum. -12 is the smallest output. So here, we can say, this is the smallest number out of all the outputs, so we can say f of xy has an absolute maximum value, absolute minimum value of -12 degrees Celsius. Degrees Celsius because that's what the original function's units were. At the point -2, 4. So for absolute minimum, we found a single lowest value, -12, and that's the point at which we found it. Katie, you notice something interesting though, which is that looks like we have 2 different absolute maximum values going on. Oh, thank God, Dr. Young was observing me. So good job, y'all put on a good performance. Katie, you made an interesting argument though. Looks like we have 2 absolute maximum. Is that okay?
I feel like that is okay.
Oh, okay then. Why is that okay?
Well, I mean, it's the same values. You could say that the absolute value is 9. But I guess it would present 2 different.
I think that's a good way to put it. That we still have a single absolute max value. There's a single temperature at which we can say is the hottest temperature at any point on the plate. It just happens to occur at 2 different points. We sort of have a tie for, here are the 2 points on the plate where the plate happens to be the hottest. And so f of xy is going to have an absolute maximum value of positive 9 degrees Celsius at the points -3, 0, and positive. It's totally okay to have the absolute max or absolute min occur at multiple points, plus you. The thing is, you can only have one absolute maximum value. It comes from the fact that when we originally defined absolute max, we said f of x has to always be less than or equal to f of a max, if a max is the place where we have an absolute maximum. The less than or equal to allows for there to be multiple values of a max, where the one absolute max value, meaning output of the function, occurs at multiple points. Hottest point occurs twice, in other words. So that's the process. We have to, given some compact set t and some function f that's continuous over it, in order to find where you have an absolute max and absolute min, you have to find critical points inside of t, find the corners of t, go along each of the boundary pieces, in this case we had 3 since t was a triangle, and look for critical points along each boundary piece by restricting, like plugging in, what does the function give us when y equals 0, or when x equals -3, or when y equals 3 minus x. We found our critical points that way, and then when we did that, we then can make a table out of all of those 3 possible types of values, because extreme value theorem tells us absolute max, absolute min needs to occur at one of these 3 types of points. And whatever gives you the biggest output, there's your absolute max. Whatever gives you the smallest output, that's your absolute min. If this is a quiz question, there would be fewer points to check. It would be a little bit easier. Or I could potentially ask for only part of it. Like, here's a function, here's a set, find all of the critical points that happen to lie along the boundary pieces. And if I did something like that, then you would only have to go through this last step. By the way, I like how we spent like a good half of class today finding these 3 points, and then none of them mattered. None of them were the absolute max and min were among the 4 points we found at the very end of Monday's class. The point is, though, they could have been the location of absolute maximum and minima, so we needed to check for these types of points. It just so happened that in this example, they didn't give us any. So, what questions or comments do you have about this whole process? Yeah, Laura?
So, if the boundary was a circle, how would you find the points on the boundary?
Ooh, if our boundary was a circle. Can you give me an equation for a circle?
X squared plus y squared equals 9.
Okay. So you want to take a circle of radius 3 about the origin. X squared plus y squared is equal to 9. So then what you would have to do, Lord, is, let's say, I don't know, f of xy is 2x plus 3y. It's just a quick little example. What I would do in this case, you would have to solve one of these for x or y. So maybe we could get something like y is plus or minus square root of 9 minus x squared. And then you would have to take what is f of x comma plus or minus square root of 9 minus x squared. It's 2x plus or minus 3 square root of 9 minus x squared, and then have fun finding critical points of that. Basically, it would get very complicated, and I'm probably not going to give you one like that. But that would be how you would do that. You would just have to use the equation for your circle, x squared plus y squared equals 9 in this case, and then solve for one of your variables, and then plug that, and then substitute that expression into your function f of xy. It's a good question. And while circles are pretty simple shapes overall, they make for very nasty absolute max, absolute min problems. Whereas compared to something like a triangle or a square is even easier. It's just all the sides are x equals constant or y equals constant. That would make it a little bit easier to deal with. Any other questions? I'm playing with their hair in a confusing way. So, you should be aware in all of these different contexts of the different ways in which these could occur. And if this is a question on a quiz, I might ask you to do the whole thing if it's a pretty simple shape. I could ask you to do part of this, or I could even ask something as simple as, hey, here's a set S. Is this set compact or not? And do we know if a continuous function will have to have an absolute max or a min here? A lot of different kinds of questions I can ask. Ooh, I can hardly wait to write quiz and exam questions. But in general, I will not try and write. In general, it is very easy to make very hard, difficult versions of this sort of question, and I won't make one in that one. Dr. Young's gone, right? I can let you out 4 minutes early. So there is a question at the back of this packet I encourage you to try out, because these are tough problems. I think it's good. I think before the quiz next Wednesday, you need to spend some time practicing a couple of them. I'm also going to post some questions from the book on Blackboard that you can try out as well. And I'd be happy to talk with you about any of this. Yeah, if you have any questions, feel free to stop by my office hours tomorrow or next Tuesday, or send me an email and we can talk some more. Right, hope you all have a good rest of your day. I will see you all in a week from now. Have a good Easter.